Welcome back to our session. We are still looking at revising redox reactions, but now we'll focus our attention on specific problems that actually demand that we apply the standard reduction potential tables and see how exactly we actually go to do that. So it's more about the technique. So we're not going to memorize the table, but what we're going to do, we'll actually try and understand how we apply the table of standard reduction potentials. In this question, it says the two unbalanced, I'm going to underline that because that's very, very important, equations for reactions involving sulfur dioxide are given, right? So there are two reactions here, okay? There's reaction one, okay, where sulfur dioxide reacts with hydrogen sulfide, and in the second one, where sulfur dioxide reacts with potassium permanganate, right? Now, it says here, what is the oxidation number? So this is about oxidation number of manganese in manganese sulfate and in potassium permanganate. So this is about chemical formula as well. But because focus is on oxidation numbers, this takes us to the rules of assigning oxidation numbers. So in manganese sulfate, here we are. We know that the total of a compound, which is a pure substance, is equals to 0, right? So if the total is 0 in this case, let's let's use the oxygen, which has got a unit of -2, unit oxidation number of -2, right? So if there's 4 atoms per formula unit there, then it means the total for oxygen is -8, right? And then potassium, as a group 1 alkali metal, it is in its combined state. It has got an oxidation number, a unit oxidation number of +1, right? So then what is the oxidation number of manganese in this case if the total is 0? So we are saying that +1 -8, what is it? So we need to find the one for manganese in this case, right? So if oxygen is -8 and then potassium is +1, we're asking ourselves, what is the oxidation number of manganese in this case? One would say, okay, let it be X, okay, whatever that is, all right? So if that's the case, it means here this X is actually +7. So because where is the 7 coming from? So if we say 1 plus this X minus 8 is equals to 0, okay, you'll get -7, which is X is equals to +7. So in potassium permanganate, the oxidation number of manganese is equals to +7. Okay, what about in the manganese sulfate, which is MnSO4? Again, the total is 0. Okay, oxygen -2, right? Sulfur is +2 in this case. So if we have that, we are saying that oxygen, in terms of oxygen, -2 multiplied by 4 of those atoms, which is -8, right? And then sulfur is always 2-, okay, which is -2 or +2 rather, okay, because oxygen is -8, and then manganese is what we don't know. Now let's look at the oxidation number of manganese in manganese sulfate, right? We're going to apply the same rules of assigning, oxidation numbers. Now, the total in this pure substance, which is a compound, is equals to 0. And what do we know? In terms of oxygen, the unit oxidation number is -2, right? It's -2. So there is 4 of those oxygen, so hence the total for oxygen becomes -8, right? So it should give us a total of 0. But sulfur is going to be +2, right? +2 in its combined state. Now we are looking for the oxidation number of manganese. So let that be X, right? So if that's the case, what are we saying here? What we have in this case, our X, which is the oxidation number of manganese. There's only 1 atom of manganese in this case. So this gives us -6. Then it will be +6 on the other end. Okay, so in manganese sulfate, this is +6, but in potassium permanganate is plus 7. So what has happened to manganese in this case? It is actually gained electrons because it changed from plus 7 rather, to plus 6, okay, according to the equation of the reaction, right? Okay. Now, is manganese oxidized or reduced? So what do we have here? We agreed that if we can quickly go back, in potassium permanganate is plus 7, right? In potassium permanganate, manganese is plus 7, but in manganese sulfate is plus 6. What has happened here? The oxidation number has decreased. So manganese is actually reduced. So what has happened to manganese? If we can represent this, we can say manganese 7 plus 7, okay, right, plus an electron to give us what? Manganese 6 plus, okay, or plus 6, okay. So in this case, it says it has been reduced because it has gained electrons, right? Okay. Now, having said that, we can then move into the next question, which says write down the oxidation half reaction for reaction 1. So oxidation in this case has to do with the loss of electrons. Right, let's look at, in this case, what is happening. Sulfur dioxide, in sulfur dioxide, oxygen is -2, and then here, this one is +2, okay? So in this case, sulfur is +4. If we can determine that it's +4 in this combined state, and then here it's 0, okay? So oxidation has to do with loss. But again, this sulfur, in this case, is, if this unit hydrogen is +1, and then this means it's +2, right? So if you look at the +2 to 0, that is the gain. But if we look at from +4 to 0, again, it shows that there was actually gain of electrons. Now we ask ourselves, which of the substances are actually, are involved in oxidation? And oxidation has to do with loss of electrons. So that's the main idea. So in terms of responding to this question, you must understand that you need to highlight the key words. So oxidation has to do with the loss. So the half reaction that we're going to come up with actually involves the loss of electrons, right? So these are just some of the, skills that are very important. And then it says here, use the table of standard reduction potentials and write balanced net ionic equations for reaction 1. Show the half reactions. So we need to draw our attention to the standard reduction potential tables, okay? So we need to identify the correct reaction. So in this case, we are saying we need the sulfur to be one of the products, and sulfur dioxide needs to be one of the reactants on the left. So this is the overall reaction. So this is the net ionic reaction. So the question wants us to use the table of standard reduction potentials to actually determine. So which equation are we going to use? We need to go back to our table of standard reduction potentials and identify the relevant one. So this is the first part of the table, and then in the second part we have these which has to do with sulfur dioxide. It's very important to analyze the equation first before you actually write the correct one. So this is the table which will always be given in an exam. So if you draw your attention to the table, it will take you to these half reactions. So if these are the reactions, we need to identify the correct one, right? In this case, water is a product, right? And sulfur is one of them. So if we go in this reaction, we try and choose the correct one. It should involve sulfur dioxide as one of them. So I'll take that as a reduction half reaction because there is sulfur dioxide, okay? And then, but sulfur dioxide goes with which one? It has to do with this one that has to do with hydrogen sulfide. So it means if we go that way, we are able to say, okay, hydrogen sulfide is actually our reducing agent, okay? So what does a reducing agent do in a reaction? It actually undergoes oxidation. So if we are going to represent this half reaction, we'll have hydrogen sulfide, right, giving us sulfur, okay, plus hydrogen ions, plus 2 electrons. Take note, the arrow goes from left to right. It's no longer the reversible one because we've decided that this is our strongest reducing agent as per the table. And then on our reduction half reaction, we still maintain that because sulfur dioxide is one of the reactants according to this overall reaction, we are saying that sulfur dioxide in an acidic medium, 4 hydrogen ions, protons, or ions if you choose to look at it, 4 electrons, okay, to give us what? Sulfur plus 2 water molecules. Right. So in terms of balancing, we need to pay careful attention to the number of electrons. So the number of electrons lost must equal the number of electrons gained. So the ratio is 1 is to 2. So we'll multiply this one by 2 and then the reduction one by 1 so that we have 4 electrons lost and 4 electrons gained. So if we have 4, these will cancel out each other because we've multiplied by the 2. Take note. And then what are we saying? If we multiply this by 2, it's going to be 2 hydrogen sulfide, right? Plus sulfur dioxide, okay? Plus, on the left, we'll have 4, okay? And then hydrogen ions and 4 on the right because we'll multiply 2 by that 2. So these will actually take care of each other. So we can remove the hydrogen ions. They won't be part of the equation overall because we've managed to take care in terms of the balancing. Right, so if that is the case, what do we have? We've got 2 atoms of sulfur, moles of sulfur, okay, plus, okay, in this case, we will also have water, which is multiplied by 1, okay? So we'll have 2 moles of water. Right, so this is our balanced equation as per, our reaction. So that's how exactly we use the table of standard reduction potentials to actually balance. But a lot happens in terms of the rules, right? So having said that, if I can quickly go back to that, you'll realize that this is the redox reaction, but this redox reaction is based on these 2 half reactions. And then we use the table of standard reduction potential to actually identify as to which substance is a stronger reducing agent while the other one becomes a stronger oxidizing agent. That's exactly how we apply these rules. But that said, we need to understand that when it comes to application and understanding, we need to expose ourselves to as much practice as we possibly can. But what we did is just to look at a few examples, because in terms of application, the practice becomes, a very important component of our understanding. So as a result of that, the more practice we do, the more comfortable we become in as far as the redox or any other, topic for that matter. With that said, that's the time we had for today. See you next time.